Okay, so when we last left off, we were discussing taking measurements of the proper number of significant figures. Next, we'll talk about, once we have our measurements, how do we handle significant figures in calculations? Well, a digit is significant if the following criteria are met. So non-zero digits are always significant. A zero is considered significant if it's between non-zero digits or if it's at the end of a number and after a decimal point. Now, a zero is not significant and is not counted as a significant figure if it is before the first non-zero digit, or if it's at the end of a number and not after a decimal point. Now, there are special types of numbers that are commonly encountered when you start to look at atoms in a molecule. These are known as exact numbers. These are conversion factors or numbers obtained from counting. And these have unlimited significant figures. So for example, in water, we have 2 hydrogen atoms. This number is exact. There's no uncertainty in the number of hydrogen atoms obtained by counting. I'm just physically counting objects that I see. Another example of an exact number is 10 to the third meter per kilometer. So this conversion factor has unlimited sig figs. So your conversion factors will never constrain the accuracy of your reported values from calculations. Does this make sense so far to everyone? Okay, let's keep going. So let's look at the following set of numbers, indicate how many significant figures do the following numbers have, and write each number in scientific notation. So 5.07, this 0 is significant as it's between non-zero numbers. In this next example, 0.0876, are these leading zeros significant? Are these leading zeros significant? No, they're not. They're before the first non-zero number. So we only have 3 sig figs. So we'd write this as 8.76 times 10 to the negative second. And here it's very easy to see that we have 3 sig figs. 1,560. So looking at this number, is this trailing zero significant? Is this trailing zero significant? No. Okay. So this number has 3 sig figs, and we can write it as 1.56 times 10 to the third. Notice how when we write a number in scientific notation, it becomes abundantly clear which digits are significant and which digits are not. Okay, so now that we've done an example, let's open up Canvas quiz 1.16 and let's try to work on the following 3 examples in our note set, indicate the number of significant figures for each of our measurements, and write each number in scientific notation. So let's take a moment. You're more than welcome to submit your responses via Canvas or via the chat function, and we'll discuss in about 3 minutes. And just as I noticed, so yes, the problem solving sets are not, you're not strictly required to complete them and turn them in. but they're useful preparation that I would recommend working on. We're already seeing some responses in the chat and on Canvas. We'll discuss in about another minute. Let's get a few more responses before we discuss momentarily. Okay, so let's discuss these examples. So first and foremost, this middle zero is significant because it's between non-zero numbers. This zero at the end is after a decimal point, so it is also significant. So we have 5 sig figs, and we write this as 9.0980 times 10 to the first. For this next number, these leading zeros are not significant. This trailing zero is significant. So this number has 4 sig figs, and we'd write this as 9.830 times 10 to the negative third. For 10,200, these trailing zeros are not significant. So we'd write this as 1.02 times 10 to the fourth. This number has 3 sig figs. The reason why I like writing numbers in scientific notation is because it makes it very easy to see which digits are significant, which digits are not. Does this example make sense to everyone? Any questions on this example? Okay, so let's keep going then. So when you often do calculations, you may end up in a situation where you have to round. Just as a general rule, in most cases, the calculated value cannot be more precise than the measured values used in the calculations. This is a general rule. There may be some exceptions. So in calculations, you may end up with a number with more significant figures than you should report. Thus, you have to round your answer to the correct number of significant figures. So when rounding, first and foremost, you look and you find the last significant digit. Then you look at the digit after the last significant digit. You round down if it's 4 or less, and you round up if the digit is 5 or greater. So for example, 13.5232 rounded to 4 significant figures. So we look at the 3. 3 is clearly less than 5, so we round down, and that gives us 13.52. So this answer has 4 sig figs as requested. Okay, so let's look at this next example. So we have 0.01506 rounded to 3 significant figures. So we have 1, 2, 3. So the 0 is the last significant digit. So we look 1 space to the right, and is 6 greater than or less than 5? Is 6 greater than or less than 5? Do we round up or down? We round up, and that in turn gives us 0.0151, which we can write as 1.51 times 10 to the negative second. which has the 3 sig figs as requested. Does this make sense to everyone so far? So to check everyone's understanding, let's have everyone open up Canvas quiz 1.16-1 and work on this problem in your notes. And don't be shy to submit your responses via Canvas or via the chat function. And we'll discuss in about a minute and a half. And remember, when rounding, you should still reflect the magnitude of your measurement. You may have to write some of these numbers in scientific notation.
Are trailing zeros to the right of the decimal significant or no?
Trailing zeros to the right of the decimal point are significant.
Okay.
Leading zeros, so zeros before the first non-zero digit, however, are not significant.
Yes. And trailing zeros with no decimal are not significant, correct?
Yep, exactly. They're not significant. So we're seeing some reasonable responses both in the chat and via Canvas. So checking the quiz statistics, we have a fair number of participants. So let's talk about each of these. Let's talk about each of these questions. So first and foremost, 1,350 rounded to 2 sig figs. So we box in. We look one space to the right of our 3. We box in our 5. We see 5 is greater than or equal to 5. So we round up. And that in turn gives us 1,400 that we can write as 1.4 times 10 to the third. For this next number, 0.005804, if we're rounding it to 3 sig figs, these leading zeros are not significant. So we have 1, 2, 3 sig figs. We look one space to the right, and that in turn gives us 0.00580, which we write as 5.80 times 10 to the negative third. Any questions on this example?
So, Professor,
Yes.
when we enter in the answer on the quiz, would we just do 1.4 or 1,400?
You'd enter 1,400 with no decimal point.
Okay.
Yeah. And Canvas does recognize that trailing zeros are not significant. Any other questions on this example?
Can you explain the second one again?
Yeah. So these leading zeros are not significant. So they aren't counted for a cap of 3 sig figs. So 5, 8, and 0, since this 0 is after a decimal point and after a non-zero number, it's significant. We look one space to the right and we see a 4. Since 4 is less than 5, we round down.
So we skip the 0 then.
No. So the 0 is our third significant figure. And to determine whether we round up or down, we look at the next digit past our last significant figure, and we figure out whether it's greater than or less than 5. From that, that determines whether or not we round up or down. As we
So
notice, this answer has 3 sig figs.
Mhm.
Does that make sense?
If that 4 were to be a 5, would that 0 turn into a 1?
Exactly.
Okay.
Mhm.
0, 5, 8, 0. Okay. And why is it -3? Like, so the first one was 10 to the third, and then the
Yeah.
second one is 10 to the negative?
Well, for 1400, if you're converting into scientific notation, we move our decimal point 3 spaces to the left, and that in turn gives us 1.4 times 10 to the third, because this is a number that's greater than 1. So we have a positive power of 10. Since this next number is less than 1, when we take 0.00580 and we move our decimal point, we're moving it 3 spaces to the right, and that in turn means we have a negative power of 10.
Okay,
Does that make
thank you.
sense?
Yeah,
Sure.
it does.
Any other questions? Okay, let's keep going then. So significant figures and multiplication and division. So when multiplying or dividing numbers, the product has significant figures equal to the number with the least number of significant figures. So for example, if I multiply 2.0 and 3.5, 2 sig figs is my smallest number of sig figs, so my answer will have 2 sig figs. Likewise, if I multiply 600, and notice 600 as written here has 1 sig fig. If we multiply 600 by 5.0, our answer will have 1 sig fig. So let's put this into practice. So looking at the following multiplication and division operations, 25 times 4. So we have 2 sig figs and 1 sig fig. So our answer of 100 needs to be rounded to 1 sig fig, which it is currently. If you want, you can write this in scientific notation, in which case it would be 1 times 10 to the second, and where this number has 1 sig fig. Let's look at this next example, 2.59 times 2.0. Okay, so we have 3 sig figs and 2 sig figs. So if we multiply it out, we get 5.18. We then look at our last significant digit. We want 2 sig figs in our answer. So we look one space to the right. 8 is greater than 5. So we round up to 5.2. In this next example, 2.000 has 4 sig figs. 3.0 has 2 sig figs. So that in turn gives us an answer 0.66 repeating. Our answer needs to have 2 sig figs. So we look at our second significant digit. We look one space to the right. And of course, 6 is greater than 5. So we round up. If we want to write this in scientific notation, it would be 6.7 times 10 to the negative first. Do these examples make sense to everyone?
So will it always be 2 sig figs ultimately? So we're always rounding it to 2?
Not always. It's just because in each of these cases, the least number of sig figs were 2. So you always round your answer to the least number of sig figs among the 2 numbers that you multiply or divide.
Oh, okay. Okay.
Okay, perfect. Any other questions I can address? If not, let's try this out on the following examples. So this is found in Canvas quiz 1.16. So this will be our second problem solving exercise in this module. So let's try to report the following answers to the correct number of significant figures. And you're welcome to submit your responses in the chat or via the Canvas quiz feature. And let's take about 3 minutes to complete this set. And don't be shy to message me with questions about any of these problems. And we'll discuss in about a minute and a half. I noticed what happened. When it copy pasted, the answers were from a previous version of the problem that I made. I fixed the key in Canvas now. So both of them should be corrected. So let's discuss these examples. So first and foremost, 0.0505 has 3 sig figs. 5.000 has 4 sig figs. So then if we divide, we get 0.0101. The least number of sig figs among 3 and 4 is 3 sig figs. Looking at this answer, it does in fact have 3 sig figs. You can report this in scientific notation as 1.01 times 10 to the negative second. And there we go. Does this make sense to everyone?
Wait, so why is it 3 sig figs for 0.0505?
Because the leading zeros are not significant.
Okay, so the first zero is not significant, and then what about the zero after that?
So the 2 zeros that are before the first non-zero number are not significant.
Okay.
The 0 in between 2 non-zero numbers is significant. So we have a total of 3 sig figs. And as a result, our final answer must have 3 sig figs, because 3 is the least number of sig figs among our 2 values that we've divided.
Okay, so if the zeros are after the 5 or a number, then those are significant, but if they're before, they aren't?
If they're after a number
Mm-hmm.
and after a decimal point, then yes.
Okay.
Mhm.
Thank you.
So let's look at this next example, 650. How many sig figs does 650 have?
Three.
So it has two sig figs because this trailing zero is not before a decimal point, so this trailing zero is not significant. So 650 has two sig figs, while 1.00 has three sig figs. So our answer needs to have two sig figs. So you can write it as 650, which has two sig figs. Or you can write it in scientific notation as 6.5 times 10 to the second. Both are valid. Does this make sense to everyone?
So the answer for the first one, is it the 1.01?
Yes, 1.01 times 10 to the negative second. Both of the ways that we've wrote our final answer are valid. Both of our depictions are valid. So it's really up to preference how you want to present it.
For quizzes and exams, is it all going to be on Canvas where we just have to write it in its full numerical form and not scientific notation?
Yes, there may be some quizzes or exam components where you'll have to submit a photo of your work on a piece of paper,
Okay.
in which case you can present it either way. But for Canvas, Canvas only really accepts effectively the long form numbers.
Okay, and for the ones that we will show our work, you'll let us know, right, whether you want it.
Yes, yeah. Mhm. Any other questions I can address?
For the first one, it said I got it wrong.
Yeah, there was an error in the Canvas key. I just corrected it.
Oh, okay.
Yeah, it's just because I was thinking of changing up some of the numbers, and the answer key didn't change when I went through and corrected that. So it should be all set now, and don't worry, you'll get full credit for this. Okay, so let's do a few more examples, this time with addition and subtraction. And this is the one that often catches students and really where you see very odd things in the lab reports. So when adding and subtracting, you retain the least number of decimal places. So not sig figs, decimal places. This is to account for the fact that all these sig fig rules are a placeholder for more detailed error analysis rules that are covered in instrumental analysis classes. So first and foremost, for addition and subtraction, you're going to write each number and you want to line up the decimal point. If there is no decimal point, you're going to place a decimal point at the end of each number. Now, if both numbers do not have a decimal place, then you're going to align the last reported significant digit. You're going to find and indicate the number with the least number of decimal places, add and subtract as normal, and you're going to round the calculated result to the lowest number of decimal places. So for example, in this first case, we have two numbers. The first number has 4 decimal places. We don't care about sig figs for addition and subtraction. We care about decimal places. The second number has 1 decimal place. So then our final answer needs to be rounded to 1 decimal place. Likewise, in this second example, we have a number with 3 decimal places and a number with 1 decimal places. So we need to round our final answer to 1 decimal place. Does this make sense to everyone? Let's do a few more examples just to illustrate this idea. So in this case, we have a number with 2 decimal places, a number with 1 decimal place. We subtract, we get 5.06. We need to round it to 1 decimal place. So that in turn gives us, after rounding, since when we look to the right, 6 is obviously greater than 5, so we get 5.1. For this next problem, we have 2 numbers with 0 decimal places. So that in turn gives us 500, but we need to respect the fact that this last column is significant. So we'd report it as 5.00 times 10 to the second, or 500 dot. Both methods are valid. So let's do another example here. So in this case, we have two numbers, each of them with 2 decimal places. So when we subtract, we have 0. So we subtract, we in turn get 0.52. Notice how in this case, we quote unquote lost sig figs during subtraction. This is normal, and this can occur quite commonly. The key thing to keep in mind is when you're adding and subtracting, you only care about decimal places, not sig figs. Let's look at this final example. So first and foremost, we identify the last significant digit. So in this case, the 2 is the last significant digit in 120. So we're gonna report up to the tens place of precision. So that in turn gives us 1,467, which we round to the tens place, and that gives us 1,470, or 1.47 times 10 to the third. So essentially you're rounding to the least number of decimal places or the smallest whole number place if your number doesn't have a decimal place. Any questions on these examples? Any questions on these examples? If not, let's test our understanding with a few problems. But before that, let's talk about another way of handling numbers without a decimal point. So one trick is to write the largest number in scientific notation. So we'll write 1,750 as 1.75 times 10 to the third. Notice I get rid of any non-significant zeros when I convert my number to scientific notation. And then we write the other number in base 10 notation with the same power of 10. So 560 is equivalent to what times 10 to the third? So to do that, we move our decimal point 3 spaces to the left, and that gives us 0.56. So we have 0.56 times 10 to the third, and now we just subtract these two numbers as normal since they have the same power of 10. Both of these numbers have 2 decimal places, so that in turn gives us 1.19 times 10 to the third, which we then write as 1,190 if we wanted to report a long form number. Notice we're still reporting up to the tens place, so both methods are valid. I personally find converting numbers into scientific notation and base 10 notation makes it easier to apply these addition and subtraction rules. Does that make sense to everyone? Any questions on this? So let's do a few more guided examples. So let's show some addition and subtraction examples. So 1.67 minus 0.71. Both of these numbers have 2 decimal places. So after subtraction, we end up with 0.96. So 5,300 minus 700. We're going to write this as 5.3 times 10 to the third minus 0.7 times 10 to the third. We see both of these numbers have one decimal place. So we get 4.6 times 10 to the third. Wonderful. So 50.4 minus 5.46. 50.4 has one sig fig, 5.4, sorry, one decimal place. 5.46 has two. So upon subtraction, that in turn gives us 44.96. Looking at 44.96, we need to round it to one decimal place. So we look to the right and we round up, and that in turn gives us 45.0. Does this make sense to everyone? Are there any questions on these examples? Okay, so let's take a moment and let's work on the following two examples. And these can be submitted using the problem solving session quiz 1.16-3 on Canvas. So let's take about 3 minutes to work through these examples, and you're free to message me your responses in the chat or provide your responses via Canvas. And I already see some reasonable responses in the chat. Let's get a few more before we discuss in about another 2 minutes. And we'll discuss in about another minute. So let's discuss now. So we have 500.245 minus 0.111. Both of these numbers have 3 decimal places, and that in turn gives us 500.134. Perfect. Oh, whoops, sorry. This is addition. Sorry. Let's add these numbers together. So 500.356. Perfect. So we have 60.13 plus 5. So this number has 2 decimal places. 5 has 0 decimal places. That in turn gives us 65.13. If we round to 0 decimal places, 1 is less than 5. So we round down, and that in turn gives us 65.
Wait, is a 5 under the 0?
Which one?
60.13 plus 5.
Yes, the 5 is under the 0.
Okay, but we don't put any decimal, right?
I mean, you could put a decimal point at the end of the 5 and just show that there are 0 decimal places if you prefer. Does that make sense?
Yeah, and why is it only 65?
Because so after adding, you get 65.13.
Mhm.
Since 5 has 0 decimal places, we need to round to 0 decimal places. So we look to the right of 5, and 1 tells us that we round down. So that in turn gives us 65. And you can put a decimal point at the end if you want. So this number has 2 sig figs and 0 decimal places, which matches the least number of decimal places in the 2 numbers that we added together. Does that make sense?
Yeah, thanks.
Perfect. So let's talk next about how we can combine these rules together. How do we combine these rules together? So for example, when you do addition, subtraction, multiplication, and division, first and foremost, you need to follow order of operations. I believe the acronym is PEMDAS. Parentheses, exponents, multiplication, division, addition, subtraction. And you follow these significant figure rules for each step. Now, it's really important, especially when doing multi-step calculations, that you don't round off at the end of the calculation. You want to make sure to carry through as all of your digits and then round only at the end of the calculation. You only round once you're completely done with your entire set of calculations. That's to minimize rounding error. So you may ask, how do I carry through these non-significant digits? So non-significant digits are carried through and noted with subscript notation or bar notation. So for example, this number, this 7 is not significant if it's written in subscript notation. So this number has 2 sig figs. Another way that you can indicate this is for 457, you can put a bar over the 5, which indicates that 5 is the last significant digit. Both methods are utilized. It's really up to personal preference. So to show how this works, let's look at an example where we have to do a set of operations. And I'll get out my calculator for this. One moment. Perfect. I have my calculator set up and ready to go. So we're going to take 4.04 plus 143. Since we're doing addition, we care about decimal places. So we have 2 decimal places, 0 decimal places. So we get 147.04. I'm going to put a bar over the 7 because our answer needs to have 0 decimal places. Okay? Let's do another addition process. So 3.550 plus 5.4090. So we have a number with 3 decimal places, a number with 4 decimal places, and we get 8.959. We've already rounded it to 3 decimal places. Thankfully, there's just a 0 at the end. And now we're going to multiply these 2 numbers together. And this is where you need to be really careful. So we have 147.04 plus 8.959. And my question to all of you is, how many sig figs does this 147.04 have as written? As written with bar notation. How many sig figs am I actually representing here? 3, exactly right. This number only has 3 sig figs as represented here. 8.959 has 4 sig figs. So then our final output answer needs to have 3 sig figs. So we enter the full 147.04 into our calculator times 8.959, And that in turn gives us 1,317.33. We're going to round it to 3 sig figs. So we look to the right. That gives us 1,320, which we can write as 1.32 times 10 to the third. Does this make sense to everyone, how you handle numbers through multi-step calculations? Any questions on this example?
Wait, so why is it 3 sig figs for 147.03?
Because after our first operation, we have a number that should have 0 decimal places. So we note that this 7 is the last significant digit. So this 147, what this bar is saying is that after the bar, those digits are not significant. So the 1, the 4, and the 7 are significant. So in total, we have 3 significant figures. Does that make sense?
Yeah.
Perfect.
I'm not understanding how we got the 1.32 times 10 to the third.
So 1,320, if we move our decimal point to get a number between 1 and 10, we move it 3 spaces to the left, and that in turn gives us a power of 10 to the third.
Oh, okay.
Does that make sense?
Yeah, because the decimal has to go after the first digit.
Yes.
Okay.
Mhm.
Could we go back real quick to up like when 65 was the sig fig?
Mhm.
I just had a question. I don't know if I'm just being silly, but because we base the number of significant figures on like the least amount, correct?
Yes, but in this case, it's the least number of decimal places. For
Okay, because the 5 is like just one number.
It's because the 5 has nothing after the decimal point. It has no decimal places.
Okay,
Mhm.
that makes sense.
So the rules for addition and subtraction are different than multiplication and division.
Okay.
Mhm. So let's do a few more examples. And I'd like you to tackle the following set of 4 examples. And I'd like you to report your answer to the correct number of sig figs. You may have to use bar notation for many of these. So let's take about 5 minutes to work through these examples. And you're more than welcome to submit your responses in the chat or via the Canvas quiz function. And we'll discuss in about 5 to 6 minutes.
Sorry, which quiz is this?
This is, one moment. This is 1.16 dash, one moment, let me pan up. Sometimes OneNote is a little bit slow. 1.16-4.
Okay.
Hey, Professor, I have a question for the first one.
Mhm.
So you said to go about it with PEMDAS, right? So for this one, we would do the multiplication first.
Yes, exactly.
So since we're doing this, it would only be the 2 or the 1 sig fig because of the 2.
Yes.
But you told us not to round till we do the final.
Yes, exactly.
So would we keep it as 10.8 and then add the 6?
Yes,
But still
but
keep
you're
it.
going to use bar notation to note what digits in that 10.8 are significant.
Okay, so then it would just be the 1.
Yes, exactly.
Okay, cool.
Mhm.
Thank you.
And if there are any other questions, don't be shy to ask. We'll discuss in about another 4 minutes. And I'm checking to see how everyone's responding in the chat and via Canvas. And especially for these problems, you have to be pretty careful. Let's try to get a few more responses in the chat and via Canvas, and then we'll discuss momentarily. Let's get a few more responses and then we'll discuss in about 2 minutes. And it's good that we have a wide array of responses. These questions are a little more involved than some of the other questions. And you just had to be really careful keeping track of your significant figures throughout these processes. And if you could specify what number when you're providing your response, I can give a little bit more feedback. So we see a wide range of answers. So let's discuss each of these problems step by step. So in this first example, we're doing multiplication first. So we have 5.4 times 2. The top number has 2 sig figs, 2 has 1 sig fig. That gives us 10.8. We're only allowed to report 1 sig fig. So 10.8, only the 1 is significant. So when we add 6 to it, this number we can report only up to the tens place, while 6 only reports up to the ones place. So then when we add our numbers together, we get 16.8. And if we round to the tens place, that in turn gives us 20. So the key thing for these multi-step operations is you need to follow the significant figure rules for each step individually. Does this first example make sense to everyone? It's slightly tricky. These are really designed to test detailed understanding of the significant figure. Yes, did someone have a question?
So,
Yeah, oh, go ahead.
you can go, it's fine.
No, I'm not understanding the tens place. So from the 10.8, okay, so we got 16.8. So why is it 20?
Because in this 10.8, only this 1 is significant. So for example, let's recontextualize this problem. So if we have 1.08 times 10 to the second plus 0.6 times 10 to the second, if only this 1 is significant, this number really has 0 decimal places functionally. Well, this bottom number has 1 decimal place. So then if we get 1.68 times 10 to the second, and we round this number to 0 decimal places, we get, times 10 to the first. So then if we round this number to 0 decimal places, we get 2.2, just 2 times 10 to the first, which is equivalent to 20. So remember how when we focused on addition and subtraction, you retain the least number of decimal places, or you retain the number with the largest last reported digit. So for example, the tens place is less precise than the ones place. That's why I like when I'm adding numbers where I don't have a clear decimal point. I like to rewrite my numbers in scientific or base 10 notation and then look to see and compare the number of decimal places. That makes it very easy to notice that this 10.8 only has 1 significant digit and it has 0 quote unquote decimal places. That's why we're only able to report up to the tens place rather than the ones place. Does that make sense?
I mean, kind of, not completely. But...
So rounding to 17 is not correct. It has to be up to 20.
Because 17 would have a digit in the ones place, and you're looking at your two numbers. 10.8 only has a significant figure in the tens place.
Okay.
Does that make sense?
Yeah.
So let's look at it. Yes, go ahead.
How do you know when to add the bar on top of a number?
So the bar indicates the last significant digit. So in our multiplication operation, we need an answer with 1 sig fig. So we put a bar over the 1 because it's our only significant digit. Does that make sense? Like if you just did this calculation normally without an additional step, 5.4 times 2, you get 10.8, and we'd go and try to round this to 10 because we want to round this to 1 sig fig, right? But we can't round at the beginning of our calculation. We have to carry this number through. So we put the bar in front of the 10, and then we note that from this point onward, this 10.8 can really functionally just be thought of as 10. It only has 1 sig fig. But we carry all of these digits through to avoid rounding errors. Does that make sense?
Yeah.
Okay, perfect. So let's look at this next example. So we have 500 times 3.0. How many sig figs does 500 have as written? 1, exactly. 3.0 has 2. For multiplication, we care about sig figs. So that in turn gives us 1,500 that we note should only have 1 sig fig. So we put a bar over our first significant digit. Now we take 1,500 and we add 4.5. So we have a significant digit in the thousands place, and we have a significant digit in the ones place. So we get 1,504.5, and we have to round to the thousands place. or round to 1 sig fig in essence. And that in turn means we look one space to the right. 5 is greater than or equal to 5. So we round up to 2,000. Does this make sense to everyone so far?
Yes.
Okay, perfect. So let's look at this next example. We have a subtraction operation in parentheses, so we have to deal with that first. Both of these numbers have 1 decimal place, so we get 0.9. Okay? We don't have to do any weird bar notation because 0.9 has the correct number of decimal places, has 1 decimal place. Now we're going to take 0.9 and multiply it by 2.0. Now, just as a question for everyone, remember how I discussed losing sig figs during subtraction? How many sig figs does 0.9 actually have to its name? How many sig figs does it have? 1. 2.0 has 2 sig figs, so when we multiply them together, we get 1.8. We have to round 1.8 to 1 sig fig. So we look to the right and we round it to 2. Does this make sense?
Yes.
Perfect. So let's look at this next example. So we have 15 divided by 20.00 minus 5.00. Okay, so let's deal with our subtraction operation first and foremost. So after subtraction, both of these numbers have 2 decimal places. We get 15.00. Okay, now we'll divide. We have 15 divided by 15.00. 15 has 2 sig figs. 15.00 has 4 sig figs. So in the end, our output needs to have 2 sig figs, so we'd report it as 1.0. Any questions on these examples? Any questions on these examples?
But why does the 5.00 have 2 sig figs?
Oh, it's not 2 sig figs. Since we're subtracting, it's decimal places.
Oh, decimal, okay.
Mhm. Subtraction cares about decimal places. Multiplication and division care about significant figures. Does that make sense?
Yeah.
Perfect. So let's talk next about ways that we can talk about data. So there are 2 major ways to talk about data: precision and accuracy. Accuracy, quite simply, is a measure of how close the average experimental measured value is to the true or literature value. So practically, we assess accuracy, the way that you'll assess it in many labs, is percent error or percent difference. So percent error is the true value minus your average experimental value over your true value. Keeping in mind that percent error is absolute, and as a result, percent error is always going to be a positive number. Unfortunately, in many cases, the true value is not known. So precision is a way of sort of looking at a data set without necessarily knowing what the true value that you're trying to measure is. So precision is the variability or deviation in a data set. Measurements with a large number of significant figures are considered more precise. So for example, if we look at 50.0, so 50.0 is plus or minus 0.1 centimeters, and 50 centimeters is plus or minus 10 centimeters. So as we can clearly see, the number with more sig figs, so 3 sig figs in 50.0 versus 1 sig fig in 50, the number with more significant figures has a smaller relative variability in its measurements. And I'll get the error corrected in the Canvas key. So let's look at a data set, for example, and we can very quickly see and notice variability in a data set. So if you look at these two data sets, which of these two data sets has the largest amount of variation? The data set on the left that I'll call A, and the data set on the right that I'll call B. Which data set has the largest variability? We clearly see that data set A has the largest variability. It's varying by a large amount relative to the average. So one way that we can quantify precision is by using deviation, average deviation, and relative average deviation. So deviation is defined as your average minus your measured value. Now we can express the average deviation among all of our data points in a data set by calculating the average deviation, which is the deviation over the number of values that you've added together. Relative average deviation gives you an idea of how large the variability is in your data set, how large your deviation is compared to your measured values. So relative average deviation is the deviation average over your average value. And you'll see these a lot in the laboratory section. So to help everyone visualize the idea of precision and accuracy, so precision and accuracy are two separate ways of describing a data set. A data set can be, for example, precise and accurate. And if we had to represent that with a target, we had to represent a precise and accurate data set, all of our data points would be closely clustered on one location, and they'd be right, almost exactly matching the true value. Our data set can be precise, but not accurate, which is a sign of potentially a reproducible error in your experimental protocol, procedure, or experimental technique, or just a reproducible error in the calculations. Just one moment, let me get this set up just right. So for example, a precise but not accurate data set would have your data closely clustered in one location, but it would not be very close to the true value. It's pretty rare for students to have those kinds of data sets without making a calculation error. Your data set can be accurate, but not precise, in which case your data set will be clustered loosely around the true value. So for example, your data set would all be averaging out to your true value, but your data set data points would not be very close to each other, will not be very reproducible. And of course, in the worst case, you can be neither accurate nor precise, in which case your data set is just a complete mess and it's all over the place. Okay, so this helps you visualize this idea that precision and accuracy are two different terms and they mean very specific things. So just be careful of this in your discussion when, and especially in the questions, When they're asking you in your lab reports, is the data precise? You should be thinking about deviation, average deviation, variability in your data set. If they're asking, is your data set accurate? You should be thinking about percent error and calculating percent error to justify your response. Does that make sense? Is everyone clear on why we're talking about precision and accuracy and why it's important to use those terms following their intended correct meaning? Okay, so let's keep going now and let's talk about density and volume. Let's talk a little bit about density and volume. So, volume is the space occupied by matter. So if we wanted to calculate, for example, the volume of a cube, it's length times width times height. And the units of volume are typically going to be centimeters cubed, also known as cc's if you happen to be in the medical profession, which is a cubic centimeter. And a centimeter cubed is equal to 1 milliliter. You should remember this conversion factor as it will be very useful. So for volume conversions, let's do an example. If 1 centimeter cubed is 1 milliliter, how many centimeters cubed are in a liter? So we're asked to go from liters to some unit to centimeter cubed. So what's our stepping stone? What's our intermediate unit in this unit conversion? What's our stepping stone for this unit conversion? Milliliters, exactly right. So if we start with 1 liter and we're going from liter to milliliter, what conversion factor? What do we need on top in our conversion factor? What do we need on top? Milliliters, exactly right. So in 1 milliliter, we have 10 to the negative third liter. And if we're going from milliliter to centimeter cubed, what do we need on top? What do we need on top? Centimeter cubed, exactly right. And we know that we have 1 centimeter cubed in 1 milliliter. Liters cancel, milliliters cancel, and we get 10 to the third centimeter cubed is equal to 1 liter. Perfect. Any questions on this example? Any questions on this example? If there aren't any questions, I'd like you to tackle the following conversion. So I'd like you to convert 450 millimeters cubed into milliliters. So this would be Canvas problem solving session 1.18.1. And don't be shy to ask questions or submit your responses via the Canvas app or via the chat. And we'll discuss in about another minute and a half. Allow me one moment. I'm going to check Canvas to see how many responses we have for the Canvas quiz. Are there any questions that anyone has via, are there any questions that anyone has on this problem solving session? If not, we'll discuss in about another 30 to 40 seconds. Let's try to get a few more responses in the chat before we discuss. It's always good to give these problems a solid attempt, just so that way when we go over the solution, you can notice any potential things to correct in your problem solving scheme. So let's discuss at this time, just to provide everyone a little bit of clarity. So we have 450 millimeters cubed, okay? So we're trying to go from millimeters cubed to milliliters. And this one requires a few steps. So how are we going to get to milliliters? How are we going to get to milliliters? What unit do we know? What unit do we know can get us to milliliters? How did we get to milliliters previously? What unit did we go through?
Liters.
You can. What's another way of getting to milliliters? Centimeters cubed, exactly. It's not to say that you can't go through liters, it's just a little more steppy. It takes a little bit more steps. So let's look at millimeters cubed to centimeter cubed. What's our intermediate unit? What's our stepping stone along the way? What's our base unit? Meters cubed. Perfect. So now I'll write out some equalities. 1 millimeter is 10 to the negative third meter. 1 centimeter is 10 to the negative second meter. And 1 centimeter cubed is 1 milliliter. Perfect. So now that we have 450 millimeters cubed, my question to all of you is, what unit needs to go on top in our first conversion? If we're converting to meters, meters goes on top. So we have 10 to the negative third meter per millimeter, and since it's a cubic unit, we cube our conversion factor. Next, we're going from meters cubed to centimeters cubed. So in 1 centimeter, we have 10 to the negative second meter. And of course, just like before, we cubed it. Finally, from centimeter cubed to milliliter, we know 1 milliliter corresponds to 1 centimeter cubed. And that in turn gives us 450 times 10 to the negative 9th times 10 to the 6th, which in turn gives us 0.450, which if we're writing following sig fig rules would be 0.45 milliliters. Does this make sense to everyone so far? Is everyone clear on how these volume conversions function? Okay, so let's take this. Any questions before we move on? Any questions before we move on? Okay, so let's take this idea and let's talk a little bit about density. So density is defined as mass over volume. Density is a physical property, and it's known as an intensive property. And these are really nice. An intensive property is a property independent of the size or amount of an object. But critically, it depends on the identity of an object. For example, a 1 gram cube of copper. So for example, 1 gram of copper has a volume of about 0.4 mils, and its density, actually 1 gram of copper has a volume about 0.2 mils, and its density is about roughly 8 gram per mil. If we look at a larger cube of copper, so 10 grams of copper, the volume will be about 2 mils, and its density again will be about 8 gram per mil. If it's pure copper, it will have the same density. That's the key point I want to make here. If it has the same chemical identity, it will, by definition, exhibit the same intensive properties. So copper, no matter how large of a piece of copper you're looking at, if it's pure copper, those two pieces will have the same density. Does that idea make sense to everyone? This is incredibly useful as it allows us to study bulk materials by looking at very small amounts of materials. Now, you can use density to differentiate substances as density is unique for different substances. So liquids and solids arrange themselves by density when mixed. The most dense species is at the bottom, the least dense species is at the top. So if we have mercury, copper, and water, mercury is at the bottom, copper is in the middle, water is at the top. Distinct chemical compounds, distinct densities. Just a side note, density changes with temperature and physical state. And typically objects expand when heated, and so their density will decrease. Okay, so how do we actually calculate density? How do we actually calculate density? Well, to calculate density, we need the mass of the object and the volume of the object. The mass of the object is pretty easy. We can just measure that with a balance. The volume of the object, it depends. Well, if it's a liquid, we can measure the volume using volumetric glassware. So for example, if a student found 10 milliliters of liquid had a total mass of 17.50 grams, we can calculate the density by taking 17.50 grams over 10.00 milliliters, and that in turn gives us 1.750 gram per mil. Notice I am respecting the sig fig rules for division. Now, in the laboratory, we often measure mass via difference. In this case, a known volume of liquid is added to an empty pre-weighed container, and the mass is found via difference. So the mass of liquid is the mass of the liquid plus the container minus the mass of the empty container. So for example, if you have your empty container, okay, and then afterwards you add some liquid. If we subtract the mass of the empty container, we can in turn figure out the mass of the liquid via difference. So let's see how this works out in practice. So let's suppose we're given an example that a student found the mass of a 50 ml beaker to be 22.500 grams. The student added 25 milliliters to the beaker, and the mass of the beaker and liquid is found to be 47.500 grams. And we're asked to calculate the density. So first things first, I'm going to figure out the mass of my liquid by taking the mass of the liquid plus the container minus the mass of my empty container. Notice you do need to follow sig fig rules for subtraction. So this gives us 25.000 grams. And now density is mass over volume. So we're going to take 25.000 grams over 25.00 mils. The top number has 5 sig figs. The bottom number has 4 sig figs. So our answer needs to have 4 sig figs. So we'd report this as 1.000 gram per mil. Make sure you are following the sig fig rules when reporting your answers for these types of problems. Does this example make sense to everyone?
No, why are we subtracting the 47.500 minus 22.500?
Because we have the mass of the empty beaker. So this is the mass of our empty beaker. And the mass of our liquid plus beaker is 47.500. So you can figure out the mass of the liquid in order to calculate the density by taking the mass of the beaker plus the liquid minus the mass of the empty beaker. So this in turn gives us the mass of the liquid. Once we have the mass of the liquid, we are given in this problem the volume of the liquid, and in turn we can calculate the density by taking mass over volume. Does that make sense?
Yeah. Okay, 25. Wait, so what's the volume? So the mass is 25.000 grams. Okay, and then
the volume is given in the problem to be 25.00, as that's how much liquid we put into the beaker.
oh, okay, volumetric pipe. Okay,
Does that
got
make
it.
sense?
Yeah, thanks.
Perfect. Okay, so let's keep going now. And now that we've seen an example of these types of problems, I'd like you to open up Canvas Quiz 1.18 and let's try to work on the following density calculation problem. So I'll give everyone about 4 to 5 minutes to work through this problem, and then we'll discuss in about 4 to 5 minutes. Don't be shy to propose your responses using the chat function or by submitting your responses using the Canvas quiz feature. And don't be shy to submit your proposed responses following sig fig rules or asking questions at this time. And we'll discuss in about 3 to 4 minutes. We're already seeing some reasonable responses in the chat and via Canvas. Let's get a few more responses and we'll discuss in about another minute and a half. Any questions? We have a fair number of responses via the chat and the Canvas quiz feature. So let's discuss the following problem. So first and foremost, we found the mass of our empty beaker to be 15.600. We have the volume of our liquid, and we have the mass of our liquid plus the beaker. So then the mass of our liquid is equal to the mass of the liquid plus the beaker, which is 35.600 grams, minus the mass of the beaker, which is 15.600 grams. That in turn gives us 20.000 grams. Now we know density is equal to the mass of liquid over the volume of liquid. So we take 20.000 grams over 10.00 milliliters, and that in turn gives us 2.000 gram per milliliter, respecting the fact the top number has 5 sig figs and the bottom number has 4 sig figs. Does this make sense to everyone? Any questions on this example?
Yeah, I'm getting confused with the sig figs because when I had divided it, it was just 2. So how does that work with the 4 sig figs?
So even though you get 2 out in your calculator, there are still trailing zeros after the decimal point. And you should include trailing zeros after the decimal point such that your output number has the correct number of sig figs. In this case, 4 sig figs.
So that's counting the 2 then? So it wouldn't be...
Yes, it's counting the 2. Yeah, the 2
Okay.
and zeros are all significant. Does that make sense?
Yes.
Perfect. Yes, so for Canvas, Canvas doesn't like trailing zeros. Canvas doesn't recognize it for some reason. So for many questions, if I'm asking for you to indicate the number of sig figs, I'll have a separate drop down for you to do that. It's just a quirk associated with Canvas. Let's now discuss another method. This is sort of a classic experiment that you probably performed in one of your previous chemistry classes, which is the volume calculated via water displacement. And we've all probably seen this phenomena in effect when, for example, if you notice a bunch of people jump into the pool or jump into a pool of water, you'll notice the water level starts to rise. That's because objects will displace or push a volume of water out of the way equal to their volume. So for example, in the water displacement method, what you do is you get out your nice graduated cylinder and you fill it with a determined volume of water or a fixed volume of water. So you record your volume initial. Okay, then, oh, whoops. One moment. Then you get an object, typically an irregularly shaped object that is not soluble in water, and it has a fixed volume that we'll call V object. We are then going to put that object into water, and at the end of this process, our water level will rise equal to the volume of our object. And we're going to call this final volume, as its name implies, V final. Okay, now we know that V final is equal to V initial plus the volume of our object. So then, if we wanted to solve for the volume of the object that we put into our water displacement apparatus, the volume of our object is equal to the volume final after we put the object in the water minus the volume of water initially. Now, if we know the mass of the object, whoops, one moment. Okay, so if we know the mass of the object, so we know density is mass over volume, so we can take our mass divided by the volume of water or the volume observed in our graduated cylinder before and after we add our solid. So we can calculate the density by taking the mass over the change in the volume. Now, one thing you need to be very careful about, you need to be careful with the significant figures for density and follow the rules for significant figures for each step. So let's talk about this next example. So a student measures the mass of a metal block. The graduated cylinder containing water before and after addition of the solid is shown below. So we are going to have to read some graduated devices. So first and foremost, I'm going to do some tick mark analysis. So from 10 to 11, it takes me 10 ticks. So 1 milliliter is equal to 10 ticks. 1 tick is 0.1 milliliters, and a tenth of a tick is equal to 0.01 milliliters. So 1, 2, 3, 4, 5, 6, 7. So this mark is about, so the third mark from the top is about 8.7. This next mark is about 8.8. So I'm going to estimate my volume, writing down my certain digits of 8.7, and then I'm going to estimate an additional digit, in this case 8.78 milliliters.
Does it have to be 8.78 or something around there?
Variation in the last digit. So
Okay.
8.79, 8.80, those are all acceptable.
Okay.
Your certain digit, however, this 8.7 is going to be fixed. That shouldn't change too much. Let's do the same volume measurement process for the after picture. So we have 1, 2, 3, 4, 5, 6. Okay, so we know our certain digits are going to be 10.6, and then we can estimate an additional digit, and I'll call that 10.65 milliliters. The volume of the solid is the difference between our final and initial volume. So we take 10.65 minus 8.78. Both of these numbers have 2 decimal places. And that in turn gives us 1.87 milliliters. Following the sig fig rules for subtraction, where we care about decimal places. Now, we're given that the mass of the solid is equal to 16.91 grams. And if density is equal to mass over volume, we're going to take 16.91 grams and divide it by 1.87 milliliters. And as a result, let's punch that into our calculator. 16.91 divided by 1.87, and that in turn gives us 9.0427 gram per mil that we round. In this case, we have 3 sig figs on the bottom, 4 sig figs on the top. So we round this number to 3 sig figs, and that in turn gives us 9.04 gram per mil. So this is an example of a complete calculation for the density of an object using the water displacement method. Any questions on this example? Any questions on this example? If not, let's test our understanding with the following example. This is found in Canvas problem solving exercise 1.18-2. You're provided two pictures of a graduate cylinder before and after the addition of marbles. I'd like you to calculate the density of the group of marbles if their combined mass is 97.394. So let's take about 6 minutes to work through this problem, and don't be shy to submit your responses via Canvas or via the chat function. And don't be shy to ask questions when working through this problem. And make sure your answer has the correct number of significant figures. And we'll discuss this example in about another 3 minutes. And the second part of this question is not, don't overthink it too much, and try to recall what kind of property is density. Let's try to get a few more responses via Canvas and in the chat, and we'll discuss momentarily. So we see a lot of reasonable responses so far. So first and foremost, we have to get our volume measurements out of the way. This is really important as this graduated cylinder has slightly irregular tick marks once again. Whoops, one moment. So from 90 all the way to 110 milliliters, it takes us 10 ticks. So then 20 mils is equal to 10 ticks. So 1 tick is equal to 2 mils. So then 1/10 of a tick is equal to 0.2 milliliters. Okay, so with that information in mind, we are past the halfway point and we have one additional mark. So our certain digits are 62. So for our volume initial, we have about 62.2 mils. The 0.2 is estimated. For our final volume, we are almost exactly at the 100 mark. So we'll write this as 100.0 milliliters. Perfect. So we know that density is equal to mass over volume. Well, first, even before that, the volume of our marbles is equal to V final minus V initial, which is equal to 100.0 milliliters minus 62.2 milliliters. That gives us 37.8 milliliters. Okay. Now let's get the mass, which is 97.394. So our density is equal to our mass over volume, which is 97.394 grams over 37.8 milliliters. The mass has 5 sig figs. Our volume has 3 sig figs. So our answer needs to have 3 sig figs. So let's punch this into our calculator. Let's get out our calculator. 97.394 over 37.8. That in turn gives us 2.5765. We look at our third significant digit. We look to the right. 6 is obviously greater than 5. So then we round up. So that in turn gives us a density of 2.6 gram per milliliter for 3 marbles. What is the density for 1 marble? What is the density for a single marble? Is it going to be the same or different? Is it going to be the same or different? This is really important. It's the same, exactly. The density is also, oh, whoops, sorry. One moment. 2.58. Sorry about that. It would also be 2.58 gram per mil. Yeah, you're correct. This should have 3 sig figs. How is the density the same? Remember that density is intensive, and it does not depend on the amount or size of an object. If it has the same chemical identity, the density will be the same.
So they're both the same answer then?
Yes.
0.58.
Mm-hmm. Because it's the same object. It doesn't matter whether you have 1 marble or 3 marbles, no matter if you increase the size of your object, if it's the same material, any increase in volume results in a commensurate increase in mass. So the density does not depend on the amount or size of an object if it's the same material. Does that make sense? Yes, the answers for the density would be different if I asked you to calculate the density of a rubber ball with the same displacement, because it would have a different mass. Exactly. It depends on the material, not on the amount of material. That's a key property of intensive properties. Okay, so we have no. The Canvas quizzes are designed to have a fairly large tolerance to account for variations in how the measurements are taken. So typically you have a fair amount of leeway.
Will the exams and quizzes be the same? Because
Yeah.
like,
Mhm.
yeah, because of the rounding and stuff like that.
Yeah, worst case, I'll go in and manually check the questions. So if something looks right, but it was marked wrong, I'll go in and check it.
Okay, thanks.
So we have completed chapter 1. We'll start chapter 2 tomorrow, and you'll see the notes posted on Canvas sometime tonight. And you'll see the next batch of problem-solving Canvas quizzes. Additionally, just as a side note, either tonight or tomorrow night, you will see the first batch of end-of-week assignments pop up. These will be due for this first week. The first batch of end of week of assignments will be due next Monday, and they'll cover all of the content addressed this week. Essentially just making sure people are keeping up with the material and are prepared for the exams. In terms of how we're going to structure the exams, once we finish around chapter 3 is when we'll have our first exam. I like to break exams up based on content rather than based on time, because the last thing you want is to have an exam that's packed with impactful concepts and an exam that's packed with not so impactful concepts. So that's our plan. What we're going to do now is we're going to shift gears. You'll see these lecture recordings posted under the chapter 1 page. Yes. The first batch has already been uploaded.